Welcome back. In the last video, I introduced this fraud detection project. Today we're doing something really important, exploring the data. Before you build any machine learning model, you need to understand your data. What patterns exist? What challenges will we face? What features actually matter? Let me tell you about this dataset before we jump into it. This comes from Kaggle, and it was created through a research collaboration between a major payment processing company and a university. The data represents credit card transactions from European cardholders collected in September 2013 over a 48-hour period. We have about 285,000 total transactions, and hidden in there are 492 fraudulent ones. This is a 0.17% fraud rate. You might wonder, why are most features just labeled V1, V2, V3? This is because of confidentiality and privacy regulations. Credit card transaction data contains extremely sensitive personal information, cardholder identity, merchant information, location data, purchase details. The researchers use PCA, principal component analysis, to transform the original features. PCA creates new features that are mathematical combination of the original ones. This preserves the patterns and relationships in the data while making it impossible to reverse engineer back to individual cardholders. Think of it like encrypting the data while keeping it useful for machine learning. Um, the only features not transformed are time, when the transaction occurred, and amount, how much was spent, because those are less sensitive. Today, I will show you exactly how I export this dataset, the visualization I created, the patterns I found, and most importantly, why those insights matter for building our models. Let's jump in. Now let's import our Python libraries. I'm importing pandas for data manipulation, numpy for numerical operations, matplotlib and seaborn for visualizations, and some scikit-learn tools we will use later for outlier detection. I also setting up a nice visualization style using the seaborn style and the hue color palette. This makes our plot looks more professional. And I'm configuring pandas to show all columns and format numbers nicely with two decimal places. Great, the library import successfully. Now let's load the dataset. So I'm loading the credit card CSV file and checking some basic informations. So look the output. We have 284,807 transactions with 31 features, 67 megabytes of memory, and it covers 48 hours of transactions. The column name includes time V1 through V28, amount, and class. Now let's visualize the first 5 transactions. Look at the data structure. Each row is a transaction, it's one transaction. So the V columns have decimal values. Those are the principal components. Amount is in euros since this is a European data. And class is 0 and 1. 0 means normal, 1 means fraud. Let's understanding the target variable. I'm analyzing the class distribution, counting how many normal versus a fraud transaction we have. look at those numbers. Normal transactions, we have 284, 3155, 315. That's like 99.82%. And then fraudulent transaction only about 0.17%, 492 frauds. This is very imbalanced, and the imbalance ratio is 578 to 1. So for every single fraudulent transaction, there are 578 normal ones. Now look at the visualization, the bar chart and the pie chart showing the distribution. It's very skewed. So if I build a real dump model that just predict the normal for every single transaction, I would get 99.83% accuracy, but I would catch zero fraud. This is called the accuracy paradox. High accuracy means nothing when your data is this imbalanced. So this will tell me three things. First, I can use accuracy as metric. Second, I need to use F1 score, precision, and recall instead. Three, I will need a special techniques like small or class weights to balance the data, the target value. So now let's check our data quality. This is always very important before we modeling. I'm checking for missing values, looking at the data types, counting duplicates, and showing statistic summaries. It's great we don't have any missing values. We have 30 flow columns and one integer column. That's our class. So we do have 1081 duplicate rows. That's actually fine in this case because people do make identical transactions. Think about buying the same coffee every morning. The describe output shows distribution statistics. Notice the mean of a class is essential zero because fraud is so real, so it barely affects the mean. Now let's look into the transaction amounts. So I'm calculating the statistic for transaction amounts overall and then comparing normal with fraud transactions. Then creating four different visualizations. So look at those statistics. The value range is from 0 to 25,691.16 cents, and the mean is 88.35, but the median is just 22. That difference tells us we have big outliers pointing up the average. So now we can compare the club by class. So the normal mean is 88.29, and the fraud, the mean is 122.21. And then if you look at the median, the normal median is 22, the fraud median is 9.25. So fraud transactions are actually smaller on average. Maybe fraudsters try to stay under the radar. So I created four different views. First one is histogram with log scale. show most transactions are small. And then the box plot by class reveals different distributions. The log transformed histogram makes the hidden patterns more visible. The fourth one is the density plot. We to show the probability distribution clear, so you can see the norm versus fraud. So you may wonder like why these four visualizations, because each tells a different part of the story. Together, they prove that the amount would be a useful feature for our models. Now let's understand when fraud occurs. Um, so we want to look the time pattern. First, I'm converting the time to seconds, from seconds to hours, because it's easy to interpret. Then creating four time-based visualizations: transaction volume over time, fraud rate over time, transaction pattern by class, and then scatter plot time versus amount. So look at those four views. The first one, transaction value over time, it shows when people transact the most. The fraud rate over time, this is actually interesting. The fraud rate varies through the 24 hours, 48 hours. Normal time distribution compares time patterns between normal and fraud. Time with a month scatter plot, I sampled 1,000 normal transactions, but showed all 492 frauds, so you can see the patterns clear. So the red dots is the fraud. Um, why I sampled the normal transactions? Because we have about 285,000 points, and the plot would be completely unreadable. So this is a more practical visualization technique. The fraud rate does vary over time, not dramatically, but enough that time-based features could help our models. So at end, I also calculate fraud rates by time of the day, um, night, morning, afternoon, evening. Those are some patterns there too. There are some patterns there too. Okay, now let's look at the PCA feature analysis. I'm calculating something called like Cohen St. It's a statistical measure of effect size. It tells us how separate the normal and fraud distributions are for each V feature. So first, I define a function to calculate the effect size. Then I loop through like all 28 V features, calculate the effect size for each, and sort them. So look at the results, the top 10 most discriminative features. So V14, the effect size is 2.26. That's really large number. And then V4 is 2.01, V11 is 1.88, V12 1.87. So any values above zero point 0.8 are considered large effects. V14 at 2.26 means the distributions are very different between normal and fraud. So now, um, okay, let's visualize those features. Those are top 10 features. So you look at the V14, the green is the normal, the red is the fraud. The distribution barely overlaps. The single feature could catch a lot of fraud. Oh, sorry. This single feature could catch a lot of fraud. So why this analysis important? It tells us like um, we have a strong signal in the data, and those are specific features like V14, V4, V11, V12, V10 are the most valuable ones. We can definitely build good models with this data. I also calculating the correlations between all features and our target value, the class. Then creating two visualizations, a correlation heat map of top 15 features, a bar chart showing the top 20 correlations. So you can look, it's, this is the correlation matrix, and this side is the top, the bar chart for the top 20 features correlated with the fraud. So the heat map in here shows which feature correlated with fraud. So V14, so you can see V14 here is V12, V10. They have a strong negative, moderate, moderate negative correlation. And then for V4, V11 have positive correlations. At the end, I check for multicollinearity, um, but I don't think here have a high correlation. So PCA is designed to create independent features. So this confirms no high correlation between the features. They are independent, so it is good for modeling now. Now let's look the outlier detection. So first, I do a sample IQR analysis on amount to find outliers. Then I use isolation forest, a machine learning algorithm designed specifically to find the anomalies on all the V features plus amount. I set a contamination to 1%, meaning I expect about 1% of points to be outliers. So look at those results. The isolation forest results detects about 1% transactions as outliers. And then fraud rate in outliers are much higher. It's like 10% here. Fraud rate in normal points is much lower. It only has 0.07%. So the improvement factor, outliers are multiple times more likely to be fraud. The scatter plot shows outliers in the time amount space. The bar chart compares fraud rates. So what does this tell us? Anomaly detection approach like isolation forest will be valuable in our ensemble later. Outliers are a strong signal for fraud. I'm printing a structured summary of everything we learned. So here's the summary. And this is the final visualization, has 9 panels summarizing everything. Class distribution, pie chart, top 5 discriminative features, among distribution comparison. So we have completed our data exploration following this Jupyter Notebook cell by cell. In the next video, we will build our first models.